In this video, we'll cover the problem number of provinces. For this question, you'll be given n cities labeled from 0 through n minus 1. So if n is 6, you'll have cities 0, 1, 2, 3, 4, and 5. You'll also be given connections among these cities, and your task is to return the number of provinces that are present. A province is just a group of cities that are connected, either indirectly or directly. As an example, this group of cities that I've circled here is one province. Even though the 0 node and the 2 node are not directly connected, we still consider them part of the same province because they are indirectly connected through the 1 node. This over here is a separate province, so the output, if this was our graph, would be 2. I'm going to be clear, this graph that I've drawn right here that I'm outlining is not the actual input for this question. I just wanted an example to show what a province is. Okay, now that we understand what a province is, let's talk about the format for this question. And it's actually not the same way that we've seen graphs structured before. The only input that we are going to receive is this grid on the left-hand side of the screen. So it's going to be a 2D array, a matrix, whatever you want to call it. And this represents the entirety of our graph. So I mentioned that we know that we have n cities labeled 0 through n minus 1. So we know that based on the number of rows present in our input grid. And that's also going to equal the number of columns in our input grid. So our cities are 0 through 5, and we can see that again with the columns. Both of these are important. And the way our input is structured is this grid tells us everything we need to know. So from the number of rows, we know how many cities we have, and this grid also tells us all of the connections between cities. So if we call this number, let's say, R, because this is the row on the left, and we call this number C, then we can say that the answer, we can say grid, let's just say it was called grid, at R, at C, should tell us, it tells us if R and C are connected. So we'll say like this is going to be true if and only if, that's what this means here, if and only if R and C are connected. So, as an example, when I say true, we can think of like our zeros and ones as booleans. So we can say it's going to be 1 if and only if R and C are connected. As an example, if we looked at, I'll circle them. So city 1 in terms of the row, and for our column we looked, no, bad example. Let's say we looked at city 3 from our row and city 4 from our column. Right here we see that their value, like when you go to grid at 3 at 4, this is a 1, which means that there is a connection from city 3 to city 4 and vice versa. We have undirected edges for this question. However, if you look at city 3 for your row and city 5 for your column, then you see a 0. This means that there is no connection from city 3 to city 5, at least no direct connection. Another way to think about it is this array, we can erase this array right here is telling us which cities 3 is connected to. And you can notice that, obviously city 3 is connected to itself. That's always going to be the case. So with this information, I want to start by drawing the graph. And that's why I have these nodes at the top here. So let's just go one node at a time. Let's focus on the 0 node first. What is it connected to? It's connected to itself, obviously. It's connected to the 2 node, and it's connected to the 5 node. So let's go ahead and pull out the 0 node, the 2 node, and the 5 node. So let's just, for now, we'll just put 0 here. We'll put 2 here. We'll put 5 here. Oops. We do not want to grab the 4. So 0, 2, and 5, like this. And we know that the connections go which way? Oh, you know what? That's okay. Actually, hold on. I did not erase the purple underline right here, and I want to make sure to get rid of that. Okay, so yes, So we know that there's a connection from 0 to 2 and from 0 to 5. So we can do this way, and we can do this way. Remember, we have undirected edges. All right, now we move on to the next node. So we have the one node. And you can see it's only connected to the one node, which basically means it's going to sit by itself. So we can just grab it and just like put it, actually we can just like leave it right here. Yeah, we'll put it here. Now we go into the next step, which is the two node. Let me grab my pen. Again, the two node right here. So it's connected to the 0 node. We've already modeled that right here. It's connected to itself, the two node, that doesn't matter, and there's nothing else it's connected to. So we've already taken care of that. The 3 node is connected to the 3 node, obviously, and the 4 node. So we want to make a connection between these two. So let's move them over here, and we can separate them a little bit to put an edge, in between them. So we'll do something like this, and we will say there's an edge from 3 to 4 and vice versa. And to be, yeah, actually that's fine. And I did the same mistake where I did not erase this here. That's okay. We'll just keep it as a small eraser for now. Okay, now, so that finishes the 3 node. We go to the 4 node and we realize it's connected with the 3 node. We'll do this. It's connected with the 3 node and the 4 node. We've already handled that, so we don't need to add those edges. We get to the 5 node. We see that it's connected to, let's underline the 5 node. It's connected to the 0 node. We already have that modeled right here. The 5 node is also connected to itself, the 5 node, and there's nothing else to model. So we've actually drawn out our graph right here. Let's just grab the whole thing and move it up. But this graph that we see on the right-hand side of the screen is the exact same thing as what you see in the input. It's just a different, in the input grid or matrix. They're just different ways of representing the same set of information. With that being said, we can talk about how we want to approach this question. We've seen this before. Really what we want to do is traverse through all of the nodes, and if a node has not been visited, we explore its group, mark it all as visited, and bump our counter by 1. We've seen that concept a few times now, so I'm not going to spend too much time talking through it. If that's confusing to you, you can look at some of the earlier problems, like number of islands, and there are several others where we use this strategy. Really what's unique about this question is the input format, so that's what I wanted to spend most of the time going over. With that being said, we can talk about the complexity of the solution. So we can write the complexity here. And we will use a DFS. I should have mentioned this, but we'll use a DFS to traverse each portion of the graph. You could use a BFS, but for this question, we'll use a DFS. So let's define our variables first. So we'll say V is going to be the number of vertices, or I guess let's use N in this case, because in the problem they're telling us that N is the number of cities. So we'll just say N equals the number of cities. And we could say E. E doesn't make as much sense here. I guess E would be the number of like times that you see ones here, because each of these represent an edge. So like you could say that if you want. I guess that is fine. Yeah, because if the entire thing was full of ones, that does increase the number of edges you go through. So sure, let's say E is equal to the number of edges. So our time complexity is going to be, I mean, we know we're iterating over every city, so it's definitely O of n, but we also know our DFS is going to be O of n plus O of n plus E. You know, same thing as V plus E, we just substituted the word. Because we know that every node is going to be pushed on the stack at some point in time, and for each node we explore all of its edges, so in total we explore all of the edges. Similarly, for our space complexity, actually not similarly, but for our space complexity, what are we tracking? The primary, well, we're tracking visited nodes, right? So every node is going to be put into, if we use a set, our visited set at some point in time. So that's certainly going to be O of n, at least. And if we think about our space complexity from the DFS, we know that it's the maximum number of nodes that are put on the stack at one point in time. And if we just had sorry about that, if we just had a single province that looked something like this, then we would have all these nodes on the stack at one point in time. So that would also be O of n as the worst case space complexity. So we can go ahead and solidify that as O of n is our worst case space complexity. All right, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. To get us started, I have our example input, the skeleton of our function, and a simple test here. We know, and by the way, I named this connections grid because the grid tells us the various connections between cities. We know we want to iterate through each of our n cities. So let's start by grabbing n, which is just going to be connections grid.length. Then first of all, we know we want to return the number of provinces. So let's do num provinces equals 0, and let's return num provinces in the end. In between, we want to iterate up through from 0 to n. So we'll say start at 0, go so long as we're at less than n, and then we'll do I++. Let's actually not name this I though. Let's say current city, just to name it a little bit more precisely. And I use Command D, the shortcut in VS Code, to highlight multiple of the same thing and change them at once. Okay, so when we have the current city, what do we want to do? Well, if the city is not visited, we want to bump our counter and make the whole province considered visited. If it is visited, we just move on. So I guess that brings an important question, which is how do we want to store our visited information? We can use either an array or a set here. It doesn't particularly matter. I will just go ahead and I'll use a set. So we'll say visited is going to be a new set. Oops. It's going to be a new set. So here, what we can say is if visited.has the current city, meaning the current city is in our visited set, then we can actually just continue. We don't need to do anything. Otherwise, we can bump num provinces because we found a new province, and then we want to mark province as visited, and we'll make a function that does this right now. But that's all for this function, other than changing the arguments here, which we will do in a little bit. So we're going to create a new function called mark province as visited, and let's see what information do we need. Well, we definitely need the grid because we have to traverse between different cities. We probably also want to know the current city for sure, and maybe n. I'm not sure right now. If we need n, then we can add it. But let's go ahead and pass connections grid and cur city right here. Okay, so we want to use a DFS, so we're going to create a stack, and we don't need to return anything. So what is our goal here? It is, we need to take the visited set as well, because we have to be updating the visited set. Duh. Okay, so what we want to do here is our goal is to traverse every node or every city in this province and mark them all as visited. So let's go ahead and push our initial city onto the stack, so current city. Let's not name it current city because we'll probably use that variable elsewhere. We can name it initial city or start city. I'll use start city because that's how I've named it in other videos. All right, so we'll say so long as the stack length is greater than 0, we want to continue iterating, meaning anything is on the stack. We want to grab out the current city using stack.pop. We want to process the node, and then we want to add all of its neighbors onto the stack. So we can say neighbors is going to be connections grid at cur city. So if we do connections grid at cur city, what happens? Let's say like this right here is 4, city 4. When you do get city 4, you get this array of zeros and ones. But really all we care about is what indices have ones, right? Because 4 is connected to 3 and 4. That's what we can tell from this line right here. And everything else is not connected. So to get the neighbors, we want to somehow filter out so that we only get a 4. So what we can do is do something like this. Let's say current city connections is going to be this entire array here. We can delete the 4 from this. It's going to be the entire array. So it's going to be this. And then what we want to do is say neighbors is going to be take this whole array, and what we want to do is filter it. Do we want to filter it? Okay, no. Here's what we're going to do. We're just going to write a separate function to say get neighbors, and we're just going to pass in the current city connections right now. We could try to do this cleverly using like a built-in JavaScript method, but I don't want to mess that up. It doesn't really matter that much how we do it. The important thing is we want to go over this array and grab only the neighbors, so the ones that we have a connection to. Then what we'll do is just say iterate over the neighbors. So for each neighbor, we want to say add the neighbor to the queue, to the stack. So stack.push the neighbor. All right, so really there's two things remaining at this point. We need to figure out how to process each node, and then we need to get the neighbors. Getting the neighbors is sort of like a separate problem, so I'm going to leave that aside for a moment and pretend like it works. But assuming that it works, we have this skeleton of our DFS. Now what we want to do at each node is mark all of them as visited. So that's pretty straightforward. We can just say visited.add, because it's a set, the current city. We also want to add some logic to make sure that we don't get in infinite loops. So if something is already visited, we should, as soon as we pop it off the stack, we should just move on. So we'll say right here, if visited.has the current city, then go ahead and continue. We could also put this on line 26 and just say don't push it onto the stack. If it's already visited, it doesn't particularly matter. All right, and I believe that's all we need to do at the process node step. Now, let's write our getNeighbors function. So we'll say, create a function that's a constant called getNeighbors. It takes a, let's just say city connections here. So we would take this whole array. And what we want to do as a comment, we want to take this and basically return 3 in this case. We're going to take the current city as well. The reason is because if, like, we're back in this example, if we're at city 4, it doesn't really matter that 4 is here. Like, I don't want to treat 4 as a neighbor, so I want to know the current city so we can ignore it. So in this case, basically what we want to do is figure out the indices of all of the ones, but don't include the current city. So what we can do is say neighbors is going to be an array and return the neighbors array at the end. And then what do we want to do? We want to iterate over city connections. So city connections dot for each city, and then index is what we're going to take. And what we want to do is this. We will say if, we'll say here has connection. Right? Yeah, because each of these is basically a Boolean telling us whether or not there's a connection. They're just represented as numbers. So we can say if has connection is 0, we just return, which in a for each is the same thing as continue. It just means like stop executing on the current iteration. If it's a 1, then we can push it into neighbors. So we'll say otherwise neighbors.push the city. No. We want to push the number of that city, which is actually its index within this array here. We don't want to just push the 1, that doesn't tell us any information. So we want to push the index here. And there's only one thing missing, which is that we don't, oh wow, what happened here? Interesting. I guess my formatter thought that 4 was supposed to be part of this, so we reformatted. Okay, the other thing is that we don't want to add city 4 when we're at city 4, because city 4 isn't really a neighbor of itself. I mean, you could argue that it is, but for our purposes, it doesn't really help us. Though it's not harmful either, but I'm just going to remove that check. So I'll just also say here, if the current city is equal to index, so basically if if we're looking at city 4 and we're on number 4, then just return. We don't want to push that onto neighbors as well. I believe that should be all for this question. Let's go ahead and test this out and see if it works. So we wanted to get, 3 is what we expected to get. I forgot for a second. So that's good. It looks like the code is working. I want to quickly go through everything again. So here we're just saying, grab the number of provinces, iterate over all of them, and whenever one hasn't been visited, say we found a new province and mark that whole province as visited. Here we are doing a pretty typical DFS for the most part. We're saying add everything to the visited set as we go. What's unique is that we have to get the neighbors in a slightly different way. In the problems we've seen before, we just have our nice graph hash map or object in JavaScript, and we can just grab the neighbors of a node from the node itself. Here we had to do a little more manipulation to, grab a subarray within our matrix and then iterate over that subarray and use certain conditions, but it's not that difficult from what we're familiar with. It's just, a little bit of array manipulation. All right, let's talk about the complexity. So we said that n is going to be the number of provinces, not spell that correctly, number of provinces, and then e is going to be the number of edges / connections. So our time complexity is O of n plus e, and our space complexity is O of n. So time complexity is O of n plus e. Well, the n you can see right here on line 58, and you can see it from the DFS because we are iterating over the entire graph, not at once, but in total, or it could be at once. But regardless, in total, we should be going through the whole graph because we go through every node. And that's why there's going to be an n, because each of those nodes is pushed onto the stack at some point in time. For each node, we explore all of its edges. So in total, we explore all of the edges, so we have this dependence on e. For the space complexity, it's O of n for two reasons. First of all, our visited set is going to contain every node by the end of our execution because we should visit every node. But also, the maximum size of our stack at any point in time, our DFS stack, would be O of n. And the worst case, if we had just a bunch of cities that were connected to each other, all as a part of one province. All right, that's all for this video, and I'll see you in the next one.